Hello, I'm Min Teacher from Seoul National University. In this talk, I will show that sequential reasoning is adequate and sufficient for establishing the soundness of compiler optimization under weak memory concurrency. Let's start with an optimization on a sequential program. Here, the source program on the left is transformed by forwarding the value returned to x for later load. We call this stored load forwarding. Since the value of x when reading from it should be 1, the optimization is clearly sound on the weak memory, under sequential semantics. What if we consider concurrency? Then it becomes non-trivial because one should consider interference by other threads at every line when establishing the correctness of optimizations. How about on the weak memory concurrency? It gets much harder, mainly due to two reasons. First, one should reason about various non-deterministic behaviors stem from an out-of-order execution. For instance, the forwarding should be sound even when the two reads from x and y are reordered. Second, weak memory models maintain complex states. For example, axiomatic models like RC11 on the left keep a graph of all memory events, and the promising semantics on operational weak memory model keeps the history of writes to each memory location. The problem gets even more complicated when validating optimizations across atomic accesses, due to varying access modes and their sophisticated semantics. Usually, we cannot expect every compiler writer to understand such complex weak memory models and reason about it. Then, how do compiler writers establish the soundness of compiler transformation on the weak memory? In fact, compiler writers usually ignore this complexity under a simple principle. According to a quote from a LLVM language reference manual here, concurrency does not matter if there is no atomic instruction. The intuition here is that a race-free program can be optimized as if it was a sequential program. However, this practice has never been formally justified under weak memory models. Moreover, it does not guarantee the correctness of optimizations across atomic instructions. To address this, our approach is to formally justify and extend this compiler writers practice. Note that we do not aim to optimize atomic instructions, but focus on non-atomics only. Nevertheless, beyond the practice, we also target optimizations across atomics, which are performed by mainstream compilers such as LLVM. Our result is a novel sequential model SEQ, and its adequacy for reasoning about compiler optimizations on the weak memory. Unlike weak memory models, SEQ is a sequential model that has no interference by other threads, is executed in order, and maintains a simple sequential memory instead of complex graphs or a history of writes. Then we prove the adequacy of SEQ in Coq, which says that all the sound optimization in SEQ are also sound in a fully weak memory model, specifically the promising semantics, or PS. The benefit is clear. In order to validate optimization on the weak memory, it is sufficient to reason about SEQ without understanding any weak memory model. Indeed, we implemented a fully certified optimizer whose soundness under PS is verified by relying solely on SEQ. This is the first certified optimizer that is verified under a fully weak memory model. We also note that our results do not rely on read-write race freedom, thereby allowing the introduction of a memory load, which actually is performed by LLVM through optimization such as loop invent code motion. Before explaining the SEQ model, I will explain the weak memory primitives used in this talk. There are two kinds of memory accesses. Non-atomic reads and writes are used for non-raced accesses. If a non-atomic reads or writes is not raced with other writes, it reads from or writes to the latest. On the other hand, raced reads retrieve an undefined value, and raced writes are undefined behavior, or UB. Notice that unlike C11, where raced reads are also UB, raced reads are not UB here, following an LLVM idiom. Atomic accesses are used for possibly raced accesses. In particular, acquired read and release writes are used for synchronization. An acquired read from a release write induces synchronization. which guarantees that every instruction before the release write is executed before every instruction after the acquire read. There are other primitives, including relaxed reads and writes, fancies, and read modify update operations, but I omit them here for the simple presentation. We assume that memory allocations are divided into atomic allocation and non-atomic ones. I will use capital X and Y for non-atomic allocation and capital A and B for atomic allocations, and lower cases for thread local variables. Now I will explain the operational semantics of SEQ. SEQ keeps a permission and a value per location. For example, as shown in the figure, a location X could have a value 7 with permission, while Y is no permission. Intuitively, permission on a location means access to the then location are not racy, so the accesses are safe. Access to a location with permission successfully read or write the value of the location, as in sequential semantics. However, reads without permission retrieve the undef value, and writes without permission are UB. Now let me explain how to validate the soundiness of optimization on non-atomics under SEQ. First on the previous store-to-load forwarding example. If there's no permission on X initially, the write to X invokes UB, and any transformation should be sound. Otherwise, the value of X becomes 1 after the write X equal 1. As expected, the read from Y has no effect on X. Thus, the succeeding read from X always reads 1. And the forwarding is sound in SEQ. Indeed, SEQ validates all the common thread local optimization on non-atomics, except for those that change memory layouts. For example, one can easily check the soundness of the following optimizations: reordering of 2 independent instructions, and elimination of overwritten stores, and hoisting out the invariant code in the loop body. The last one, also known as loop invariant code motion, is interesting in that it actually introduces the potentially race load when the loop iterates 0 times. Such introduction of the load is sound in SEQ thanks to the semantics of race loads reading the undef value instead of resulting in UB. Since we aim to validate optimization even across atomic accesses, SEQ has a special semantics for them. Intuitively speaking, SEQ abstracts other threads' interference on atomic accesses. Specifically, acquire reads are similar to log acquisition. In concurrency, by acquiring a log, the thread acquires permission to access certain locations protected by the log and sees the values written by other threads. In SEQ, when a program performs the acquire read, it non-deterministically acquires permission to some locations and retrieves new values for those locations. On the other hand, release writes correspond to lock release. When an SEQ program executes a release write, it drops a permission to some locations, as if a thread releases a lock to other threads. Consider the following example with release and acquire accesses. Let's suppose that the program initially has a permission on X. After executing the write to X, the value of X becomes 1, so the following read gets 1. Then, after executing the release write, it releases the current memory value, X to 1, and may lose permission on X. Then the later read from X will get undef, since it no longer has permission on X. Now, suppose that the acquire read from B reads 1. The program may acquire permission on X along with the new value to X, say 5. Then the final read from X will read 5 safely. Now let's see how to validate optimization across atomics using the previous example. If there is no atomic instruction, these 3 reads from X can be optimized into a simple assignment by forwarding the write to X. However, with atomic access in the program, one of the 3 forwardings is indeed unsound. As before, the write to X can be safely forwarded to the first read from X, since there is atomic access in between. Sorry, there is no atomic access in between. on the release write, the program may either lose the permission or permission on X or maintain it. For the case where the permission on X is lost, the next read from X will read on def. Otherwise, the read will get 1, the current value. Interestingly, in either case, it is sound to replace the read from X with an assignment of 1, since reading on def induces more behavior than reading 1. Suppose that the permission on X is lost on the release write. Then, after the acquire read, the program may acquire the permission on X again along with the new value, 7. In this case, the last read from X can only read 7, which makes the folding unsound. Now, I will present the Adequacy theorem, a key to the applicability of SEQ in sequential reasoning for compiler transformation under weak memory. This theorem guarantees that if a source program is behaviorally refined by a target program in SEQ, and the source program is deterministic, then the source is also contextually refined by the target under the presence of the arbitrary context threads in the promising semantics. To keep the presentation simple, I will not go through the formal definition of behavior refinement in SEQ. Roughly speaking, it is a modification of the standard trace inclusion. The formal definitions can be found in the paper. To demonstrate the applicability of SEQ for compiler verification, we developed a certified optimizer that optimizes arbitrary given programs. The optimizer first analyzes a given program and then optimizes the program using the analysis result. For example, the optimizer analyzes that in any SEQ execution with reading X, there's no permission on X or X contains value 1. Then from the result, the optimizer figures out the read from X can be optimized to an assignment of value 1. The optimizer is verified in Coq, solely relying on SEQ, following the existing approaches of verified compilers for sequential programs, such as COMSOT. Specifically, we use the simulation technique and abstract interpretation-based program analysis to prove the soundiness of the 4 optimization passes. For instance, we first show that the analysis performed by optimizer is sound in SEQ. Then, using the soundiness of analysis, we establish the simulation relation between the source and the target programs. Specifically, we verify the following optimization passes. Store to load forwarding that forwards a written value to later load, possibly after some atomic instructions that meet certain constraints. And load to load forwarding that forwards a read value to later loads, dead store elimination that removes dead store overwritten by another store, and loop invariant code immersion that hoists invariant code in the loop body out the loop. We verified that the optimized program indeed behaviorally refines the source program under SEQ. Then, thanks to our adequacy theorem of SEQ, the refinement in SEQ directly implies the contextual refinement in the promising semantics. Our result has some limitations. First, we do not validate optimization on atomics, as well as the modifying memory layouts. Furthermore, the adequacy theorem requires each thread to be deterministic. And finally, the contextual refinement of promising semantics used in the adequacy theorem is not termination preserving. Some details that I omit in this talk can be found in the paper. To conclude, we developed a sequential model SEQ for validating optimization under weak memory concurrency without understanding the underlying weak memory model. SEQ is adequate for establishing the soundiness of compiler transformation on the weak memory, in the sense that behavioral refinement in SEQ entails the contextual refinement in the promising semantics. Furthermore, SEQ is sufficient to validate compiler optimizations on non-atomics. To show the applicability of SEQ in compiler verification, we developed and verified a certified optimizer based on SEQ. Thanks to sequential nature of the SEQ, the verification follows the existing approaches of COMSOT, a certified compiler for sequential programs. Our results not only are the formal justification of compile-writer's practice, that concurrency does not matter on the soundiness of optimization on non-atomics, but also serve as a mental model for powerful optimizations across atomics. Moreover, they give theoretical grounds for future directions, such as certified compilation, train-slice validation, and testing under weak memory. Okay, this is the end of my talk. Yeah, thank you.
Those 3 points at the bottom.
Yeah.
If I was writing a compiler, not just with those 4 optimizations, but I was writing, a new version of a compiler in LLVM, would this be sufficient for me to just say, I don't have to worry about concurrency? It's all been proven unnecessary by this paper in PLDI 2022?
Oh, actually, as I said in the limitation section, we don't support transformation modifying memory layouts. And that one is needed for compilation, as for example, register promotion or register location. But without that, you can ignore the concurrency. Okay, as we shown.
Okay. Other questions?
So one of the issues that we hit doing this kind of thing is about conditionals, and in particular, if introduction and if elimination. And as far as I can see in this model, because you've got permissions, if elimination is going to be sound, but if introduction isn't, because if you do something like replace B by if X, then B else B, right, you might not have permission to read X, so that could be UB.
But reading without permission get on-def, and it's not UB. So I think that only if introduction sound in our model,
Oh, okay. So you've got if introduction and if elimination.
Sorry.
You can introduce and eliminate if.
Yeah, right.
Cool.
Other questions? Where? Oh, Rolf, sorry.
Yes, thank you. Very nice work. One thing I was wondering is, do you have any sense of completeness for this? Like if I justify all my optimizations using SEQ, are there any optimizations that will be missing besides the ones you mentioned, that I would still need the full complicated system to prove?
Okay. Oh, I'm not
Sorry
sure
sorry for the hard question.
But I don't know any optimization that is unsound in our model. Yeah, just that's all I can say.
Okay, but you also don't have any idea how you would go about proving any sort of completeness result or something? That might be. I have no idea how to do that, but it sounds maybe interesting.
Yeah, I'm not sure, but yeah.
That's fair. Thanks.
Yeah,
So let's thank the speaker.